I hope everybody can hear me. As it says, this is a report on joint work with Malabika Pramanik. I'd like to apologize ahead of time that I have very little experience with Zoom presentations, so if things get rough, I hope you'll interrupt me and ask what's going on. I'd also like to thank the organizers for the invitation to speak. Let me begin with some notation. I'm going to be dealing with, I'm going to be talking about tube domains, and the setup is that I'm going to have a finite dimensional vector space V. I don't want to think of this immediately as Rn because I don't want to necessarily choose a basis. So I'm just going to have a finite dimensional vector space with an inner product. We'll choose bases later on depending on the situation. And we're going to take a proper open convex subset sigma in V. That simply means that it's a convex set that doesn't contain any straight line. And then the tube domain is the set of points in the complexification where the imaginary part belongs to this complex, to this convex set. Of course, we choose convex sets because tube domains over a general set will be pseudoconvex if and only if the base is convex. I want to consider certain weighted spaces as well. So I'm going to consider weight functions on the tube, but I want them to depend only on this imaginary part y. So the weight functions will be given by some function that's really defined only on sigma. And then P omega and B omega are going to be the Bergman projection and Bergman kernel. I don't think this needs much explanation. A2 is the Bergman space, and then the projection is the orthogonal projection. And the Bergman kernel allows us to say explicitly what the Bergman projection does. What's gone wrong here? Okay. What I want to try to emphasize in the talk is the importance of caps of convex sets. So what is a cap? I'll try to give a more precise definition in a minute, but it's going to be the intersection of sigma with some closed half space. And what I want to look at are caps which have passing through a given point, that is that the hyperplane passes through this point P, and I want to consider caps of minimal volume. And I'm going to call that volume delta of P. And I'm also mostly going to be considering weight functions, which are given by this function delta raised to some negative power. And this is really sort of an advertisement for sort of thinking about the role of these minimal caps. What I then want to try to do after discussing these minimal caps, I want to discuss three explicit situations in which the weighted Bergman kernels can be estimated in terms of this quantity delta. So what are they? First of all, I want to show that if I take an arbitrary, absolutely arbitrary proper convex set, then we can get essentially sharp estimates on the diagonal for the Bergman kernel, for the weighted Bergman kernel. If we restrict and look at bounded convex sets, then the Bergman kernel is, I don't have to, here I'm looking at the point x plus iy, u plus iv, and so x is not necessarily equal to u. And we want to show that this has exponential decay as that difference goes to infinity. And finally, I want to consider domains, I sort of call them model domains, where I'm looking at something where a variable is sitting above the graph of some convex polynomial of finite type. And in this case, we'll get estimates everywhere, not only on the diagonal, not only as we go to infinity, but in general everywhere. And as a result, we can show that the Bergman kernel extends to a bounded map on LP. So let me sort of just begin with some elementary examples where the Bergman kernel can be explicitly computed. Two very well-known examples are the upper half space in C. It's usually a common weight function is to take y to the minus alpha, and then the Bergman kernel is given by some constant depending on alpha times z minus w bar to the minus 2 plus alpha. A slightly more interesting example, I think, is the infinite strip. Here I would take the vector space to be R, and sigma is just an interval, -1 to 1. Here I want to take the weight function to be identically 1. So this is the unweighted situation, in which case you can make the computation that the Bergman kernel is given by this hyperbolic secant squared. The reason for choosing omega identically 1 is that I don't know a closed formula for the weighted Bergman kernel in these cases. However, even in the weighted, unweighted situation, one can see explicitly in this example that there is going to be exponential decay as x minus u goes to infinity. A third example is what I might call the polarized Ziegler upper half space. So it's sort of like the Ziegler upper half space. I've written this couple of lines down, u sub n plus 1. This is the usual Ziegler upper half space with the imaginary part of zn is bigger than the modulus of the other z squared. Here I'm looking at the set in Rn where the n plus first variable lies above a parabola. And this tube, the tube over this is really biholomorphic, either to the unit ball or the Ziegler upper half space. And if we take a weight function like this expression to the minus beta, then one can compute explicitly what the Bergman kernel is, and it's given by this formula at the bottom. It looks rather complicated, but it's simply after a change of variables, it's the usual Bergman kernel in the Ziegler upper half plane. A final example is the Lorentz cone, or the forward light cone. Can one see this? Yeah. Here I'm looking at yn squared bigger than the sum of the other yj's squared, and yn positive. This is an example of a symmetric homogeneous cone. And I'm sure people have noticed that in the talks, there'll be many talks, I expect, dealing with such cones. Let me just point out that what this symmetry in this case means that the closed dual cone, which I've written here as sigma star, is the closure of sigma. And homogeneity means that there's a group of linear transformations of the underlying space Rn, which preserve sigma and act transitively. And now in this case, this is perhaps maligning standard notation, but I want to let delta in this case be yn squared minus some of the other things squared to the power n over 2. This may not be what delta is called in some of the literature, but in this case, one can check that delta, when you act by one of these linear transformation mappings which preserve sigma, it acts, delta of gy is the determinant of g times delta of y. That should be omega of y. And this, in fact, is simply a constant times the minimum volume of a cap through the point y. And in this case, the formula for the Bergman kernel is given at the bottom. So here are 4 examples. The formulas look a little bit different, but I hope one will see that somehow underlying this all are these volumes of minimal caps. So it's a little bit dangerous with so many experts listening to try to talk about some background material. The literature on all of this, there's a huge literature, but I thought I ought to mention at least a few important points. McNeil and Stein studied LP boundedness of Bergman and Ziegler kernels in bounded convex domains of finite type. There, the analysis was based on the D-bar problem, and the geometry was somehow based on maximal polydisks that could be embedded in the domain. A former student, Soledad Banguria, who studied these domains above the graph of a polynomial when P is convex, and she considered some examples like this. Gupta has studied the relationship between the sublevel sets of the Bergman kernel in for tubes over bounded convex sets, and certain floating bodies of these sets, which is the set, say, where the volume of the minimal cone is bigger than delta. And of course, there's been a huge amount of work on the LP boundedness and non-boundedness of Bergman kernels over tubes on homogeneous symmetric cones. And I've tried to list at least some of the authors. If I've left out some names, I'd like to apologize. And finally, I mentioned that tube domains are closely connected to Reinhardt domains via the Poisson summation formula. And of course, there's a huge amount of work done on Reinhardt domains as well. So there's all sorts of important background on this. So let me begin by saying that there's actually an integral formula that works for any proper open convex set and any weight function. And it's given here by this formula. This was initially discovered, I believe, by Rothaus in the case when sigma is a self-dual homogeneous cone and the situation is unweighted. Korani extended this to arbitrary convex cones, and then Rothaus established the general case. I think in the literature one sees quite often that this has been rediscovered and republished. So I point out that with this formula, one has then a formula for derivatives also of the Bergman kernel. I've considered only derivatives with respect to z. Of course, the derivatives with respect to z bar are 0, and the derivatives with respect to w bar are can be written in terms of the derivative with respect to z. So I'm simply going to stick to these derivatives with respect to z. And now let me make a point about this formula. The Bergman kernel in these tube domains depends only on the real part of the difference between z and w and the imaginary part of z plus w. And to see that, let's simply write z is x plus iy and w is u plus iv. And let's take p to be 1/2 y plus v. Y and v are points in the convex set, so 1/2 y plus v is also in sigma. And now we can write the Bergman kernel as I've written here in the third line, fourth line. I can move this 4 pi inner product of p with t downstairs. So I have this formula. This shows that the function, that the Bergman kernel only depends on x minus u and p. And if I let sigma sub p be simply the translate of sigma, and then translate omega, the weight function, similarly, then I have this formula for the weighted Bergman kernel. And the remark is that this set sigma p is just a convex set which contains the origin, and omega p is a weight function. And so this formula really shows that the study of the Bergman kernel on tubes is just the study of the Fourier transform of the inverses of some functions of this form. So that's somehow what's at the base of all of this. Excuse me a minute. Okay, let me begin by talking more explicitly about caps of convex sets. So I have a set sigma, I have a point P in sigma, and any cap of sigma is simply the intersection of the points in sigma with the half plane defined by this, orthogonal to this unit vector n passing through P. I'm going to let sigma hat be the supremum over, I'm sorry, this should be points T in V. Oh, I'm sorry, I think it's correct. So this is the set, sigma hat is a cone, and it's the set of directions in which the set sigma is somehow bounded. It doesn't go off to infinity. This is sometimes called the dual cone of sigma, or sometimes the negative dual cone of sigma. The notation varies. And the importance for us is that the volume of a cap is finite if and only if the direction n is in the interior of this cone. If I take points in the interior of this cone where I know that the volume is going to be finite, and I let these points approach the boundary of this cone, then the volume goes to infinity. And therefore, it follows that there has to be some point in the cone where the volume actually takes on a minimum. And so I'm going to call this vector E, and then this cap is going to be a cap through sigma of sigma through E having minimal volume. What one needs to remember, however, is that this vector E need not be unique, even if the point is close to the boundary. The volume, of course, is well defined, but the vector E is not unique. Simple example is to take the unit ball, then every cap through the origin has the same volume. If you take sigma to be the positive quadrant in R2, then there is a unique cap of minimum area through every point. If you look at the set of points where the volume of the volume or the area of that minimal cap is constant, it's going to be a hyperbola. And I've written down what the formula for that volume is. Of sort of interest is take a half strip, look at the set of points x, y, where x is between 0, -1 and 1, and y is positive. Then if I look at points on the real axis, that's points 0b would be positive, then actually there are infinitely many caps of minimal volume passing through this point. The minimal volume is 4b, but you can take any direction where theta is going to be the angle between the vector and, say, the positive real axis, and there's some constraint on theta. So one must not think that the cap is actually unique. It's just the volume that's unique. So now I want to talk a little bit about the geometry of these caps. So let's pick a point P, and if I take any vector, unit vector n, let's let HP be the hyperplane perpendicular to n passing through P, and let's let SP be the slice of sigma with that hyperplane. And now what I want to claim is that if the dimension of the vector space is n, and if P is in sigma, then I can find an orthonormal basis. This is why I wanted to work with a vector space V rather than with Rn at the beginning. Given P and n, given P, there is an orthonormal basis and positive constants and a point in the boundary with the following properties. First of all, this vector En, if I look at the cap through P in that direction, this will be a cap of minimal volume. Next, the point P, it's going to lie on the slice. This slice is going to be a convex set in this the intersection of sigma with this hyperplane, and the point P is the centroid of that slice. And being the centroid of that slice, it's almost as though you're using the John ellipsoid of that bounded slice. In this case, you can check that this slice is well approximated by ellipses. If I let H be this hyperplane, then the intersection is contained between two ellipses where the major axes, minor axes, the various axes are these constants mu1 through mu(n) minus 1. The constant mu(n) somehow tells us the distance between the point P and the maximum direction in the direction of En, and the volume of this minimal volume of this minimal cap is given by the product of these mu j's. This is not very hard to prove using what's known about ellipses in convex set, bounded convex sets. What's perhaps, I think, maybe not quite so obvious is to think about integrability properties of this minimal volume function. So what I want to state is the following lemma, that if the dimension is n and sigma is a bounded convex set, then we want to look at sort of sublevel sets of this function delta. Remember, delta is the minimal volume, so making delta small presumably means that our point must be get closer and closer to the boundary. And the first part of the lemma says that no matter what bounded convex set we take, then the measure of the set where this is less than lambda is bounded by lambda to this power 2 over n plus 1 times this volume of the set sigma to this power n minus 1 over n plus 1. This is really the part of the lemma that will be most important for us, but I also want to point out that one can say other things if one is dealing with either polytopes, or if one wants to look at integrals or inequalities in the other direction. Here in the first estimate, we have an estimate from above. There's a general estimate from below, which involves only lambda to the first power and a log term. And also, if sigma is the interior of a polytope, then one can actually do better than this first estimate. One gets an inequality that involves lambda and a log term as well. So where does this lemma come from? The last two statements, which involve the log terms, appear in a paper Bergman and Larman. And the first statement, which is the one I'm most interested in, follows from another result in that same paper with a result of Gromer. And I'd like to at least discuss very briefly what I think is a very interesting proof, because it proceeds via some kind of stochastic questions in stochastic geometry. So the idea is the following. You have this bounded convex set sigma, and you choose m random points in sigma. Random, they're chosen independently and uniformly distributed. And you look at the convex hull. And now you let E be the expectation of the volume of sigma minus that convex hull. And what Bergman and Larman proved is that at least if the volume of sigma is 1, then this expectation, as the number of points gets large, the number is m, that's approximated by, that is bounded above and below by constants that only depend on n, times the volume of this sublevel set. Now, if we look at the convex set being a Euclidean ball with volume 1, then it's quite easy to see that the volume of the sublevel set is given by lambda to the 2 over n plus 1. That's where this factor 2 over n plus 1 comes from. And Gromer's theorem shows that if you take any convex body, then the expectation for that convex body is bounded by the expectation for the ball. And putting these two results together, we get the estimate that we're interested in. So I found this a rather interesting way of proving this, this sublevel set estimate. Now, as a corollary, and this is one of the things that we'll be using, if sigma is bounded, then the integral of this delta function to a power minus alpha is bounded by a constant times the volume of sigma to the power 1 minus alpha, where this constant is bounded if, in general, alpha is less than 2 over n plus 1, that is for any bounded convex set sigma. But it follows from the earlier results that if we happen to be dealing with a polydisk, then this inequality holds in a larger range of alpha, for alpha less than 1. How does the proof go? Well, let's consider the case when sigma is 1. Then the set, the measure of the level set, of course, sublevel set is always bounded by 1. And so if we want to compute the integral of delta to the minus alpha, we write it in terms of the integral of the sublevel sets, which I've done in the next 2 lines. And now I break this integral up from 0 to 1 and 1 to infinity. The integral from 0 to 1 are just bounded by 1. And we now want to know when are these integrals bounded. And in general, what we need is the convergence of these integrals, which gives us the various ranges of alpha that we talked about. If sigma is not equal to 1, if the volume of sigma is not equal to 1, that was assumed here, then one can get the more general result simply by dilating the set and using the fact that this minimum volume function behaves well relative to dilations. The determinant of the linear function comes out. So how does one use that? What I want to claim is that since we want to be able to estimate Bergman kernels, we have to estimate certain integrals involving powers of y and exponentials. And so we want to know when certain things are finite. And the theorem says that the following 3 conditions are equivalent. I have T is an interior point of sigma hat, that's the interior of the dual cone to sigma. That's the set of directions in which the minimum volume is finite. I'm sorry, the set of directions in which the cap in that direction is finite. If that's finite, then this integral is finite for all lambda and all m bigger than or equal to 0. And that, of course, implies by taking m equals 0 and lambda equals 1 and alpha equals 0, that simply says this integral is 0, this integral is finite. And that in turn implies that t is in the interior. I would like to very briefly sketch the proof, not of everything, but at least that this condition, that if t is in the interior, then we have the finiteness of this integral. So why is that the case? I'm trying to prove that t is in the interior, then this integral is finite. And the idea is as follows. All of these conditions are invariant under translation of sigma. And so if we translate sigma, we can always arrange so that sigma is contained in some proper right circular cone, which I've written this way. I've split S. T is a vector, and E is the normalization of that T. It's T divided by the length of T. And so I'm looking at a right circular cone whose axis of symmetry is in the direction of T. I then choose coordinates so that the nth coordinate is in the direction of T, and I break this set sigma up into pieces by where this nth variable is between minus k and minus k plus 1. The volume of this piece is then bounded by something that involves k to a power. It's not too hard to see that that this minimum volume of a larger set is bigger than or equal to the minimum volume of a smaller set. And so now if I make this estimate, I want to make this integral that's going to be less than or equal to the sum of the integrals of the various parts. I can bound the size of S by something involving K. I can estimate the exponential by something involving K. And what I'm left with is something involving just the integral over sigma K. But now we know that this is bounded by the volume of sigma K to a power, and that's in turn bounded by K to a power, and one's end up with this finite sum. So that's the idea of that. Okay, let me then, having talked a little bit about the geometry and properties of minimal caps, let me now return to Bergman kernels, and let's now consider the problem of trying to estimate Bergman kernels on the diagonal. So again, I'm going to take sigma to be an arbitrary proper convex set. I'm going to choose my weight function to be delta to the minus alpha, where now I want to let alpha be less than 2 over n plus 1. I'm going to let the ej's and the muj's be the vectors and constants associated to a cap of minimal volume. And the theorem is as follows. If I look at the Bergman kernel on the diagonal, then the size of the Bergman kernel is bounded above and below by the volume of the minimal cap times the volume of the minimal cap times to the power minus 2 plus alpha. In particular, for the unweighted, it's simply delta to the minus 2. And if you think back to the examples that I started with, which is the upper half space or the polarized Ziggler upper half space or the cone, this agrees with the estimates I gave there. More generally, if one wants to take derivatives, then each derivative loses something. And what do they lose? Well, they lose a certain power, they lose 1 power of one of these parameters that describe the geometry of this minimal cap. Okay, let me say a brief word about where this comes from. Let's write down what the Bergman kernel on the diagonal is. On the diagonal, there's no oscillation anymore, so one simply has this integral. And now in this integral, I want to make a change of variables by a certain linear transformation. What I'm going to do is dilate everything by these parameters. Remember, the way I've normalized things now, my set sigma y contains the origin, and the origin, I'm looking at a minimal cap centered at that point, which has size in various directions, mu1 through mu(n) minus 1. And in the nth direction, it's of size mu(n), at least in one direction. And now what I want to do is normalize that so that my new set is sort of size 1 in all directions. And that's what I'm doing here. I'm making a double change of variables in this integral in this way. And what I then get, when I make these changes of variables, I get powers of the determinant of L coming out, but the determinant of L is just the volume of this minimal cap times this integral. But now this is an integral where this set, the inverse image of y, has been normalized. So this integral in the denominator is an integral over something which actually contains a ball of some fixed radius epsilon, where epsilon is independent of everything, depends only on n. And so this inner integral is bounded below by some exponentially growing function because of I have this integral of e to the the inner product of S and T. And so the integral over this outer part is bounded above by the integral over all Rn. And so I will have an integral over all of Rn of e to the minus Ct, which is bounded. So this integral is bounded. And so I have the Bergman kernel at least less than or equal to this expression. The other integral is done similarly. Now let's talk about exponential decay. Now I want to assume that my set sigma is bounded. Of course, I don't expect exponential decay in general. The simplest example of that is the upper half space, where the Bergman kernel is given by 1 over z minus w bar squared, so there's no exponential decay at all. But we did see that there is exponential decay in the case of the bounded set minus 1, 1. And so the claim is that if we have a bounded set with, say, diameter delta, I can always translate so that I'm assuming that the origin belongs to sigma. Then I get the estimate that the Bergman kernel is bounded just as before, times this power of the minimal volume to the power minus 2 plus alpha. But now one has an exponential factor involving x minus u divided by the diameter. Notice, of course, that as the diameter gets larger and larger and larger, this exponential factor gets smaller and smaller and smaller. So as if I sort of think of what happens as this strip gets larger and larger in width and becomes the upper half space, the exponential decay disappears. More generally, if I take derivatives, this, of course, is not ZW. This should be ZZ. I wish I could prove off-diagonal estimates in general, but this is a diagonal estimate of derivatives. It's the same thing as above, but again, each derivative involves a loss of one of these distances to the boundary, these parameters. So where does this come from? Oops. To take advantage of the oscillation, what one can do here is simply change the contour from integrating over t in Rn to a new constant where I've moved up or down by some amount in the complex direction. Of course, in order to do that, one needs to show that the denominator in this integral the denominator is actually going to be an entire holomorphic function, but one needs to know that it doesn't have any zeros. So one needs to find a region in which there are no zeros. And that's somehow what limits the size of how far up how big one can go up, which in turn leads to the rate of decay of this exponential decay. So I won't say any more about that at this point. Finally, let me say a few words about model domains. So what is a model domain? I'm going to look now in Rn plus 1. I've used notation where boldface y is an n-tuple of variables and little y is just a single variable. And I'm looking at domains where little y is bigger than a convex polynomial of boldface y, where the polynomial is convex and of finite line type. That just means that at any point, the tangent line to the graph makes the most finite order of contact. I'm going to this time use weight functions which are the height above the boundary to some power minus beta. And I'm going to let b sub beta be the corresponding weighted Bergman kernel. I should point out here, I'm not taking the volume of the minimal cone, minimal cap, but if the Hessian is strictly positive, that is, if I'm dealing with something with non-vanishing Gaussian curvature, then the volume of the minimal cap is just this height raised to an appropriate power, and one sees that beta less than 1 corresponds to alpha less than 2 over n plus 1, as we had before. In general, one has the volume of the minimal cap bigger than or equal to this, so one should presumably be able to prove similar theorems where instead of using just this weight function, one uses more general weight functions that also involve the volume of the minimal cap. So to state the theorem, let me introduce some notation. If I have a polynomial p, capital P, and I have a point little p in Rn, what I want to do is renormalize this polynomial capital P centered at P. What I'm doing is simply translating and sort of moving the tangent plane so that I have a new convex polynomial P sub little p, which vanishes at the origin, whose gradient vanishes at the origin, and whose Hessian is the same as the original Hessian of P, just translated by the distance P. And now the point is that if I take a point P in Rn, then what I want to look at is the set where this new normalized polynomial P sub lower p is less than 1 over R. And the point is that it's controlled above and below, well, it's sort of squeezed between two ellipses whose semi-major axes are given by these constants. This again involves somehow analysis of what this convex set looks like. And so now the theorem is the following. Here I want to write down general estimates. I take 2 points in the tube, and again I write P, capital P, or boldface P, little p, to be the average of YV, of the 2 points Y and V. I'm going to let capital sigma sub P of lambda to be the volume of the set in Rn where this normalized polynomial is less than 1 over lambda. So this is a kind of geometric quantity that somehow involves the volume of a minimal cap of height 1 over lambda. And now one introduces this parameter delta, which involves the distance between x minus u in somehow the normal direction, and this quantity in the tangent direction. This is the height of a point above the boundary, and this is the value of the polynomial at x minus u. And then we have this estimate for arbitrary zw and ww. It's given by this delta to the minus power minus 2 plus beta, and this other quantity to the minus 2. Notice that the effect of the weight function in this case is only felt in one direction rather than both. That's because our weight function involved only the height to the minus beta rather than the volume of the minimal cap to the minus alpha. More generally, if you want to take derivatives, one gets a similar statement where each derivative gains an extra. Derivatives in the tangent direction involve these parameters in the tangential direction, and a derivative in the normal direction involves a loss of 1 factor of delta. as a consequence of this, I sort of want to finish by saying that as a consequence of this, one can show that this Bergman projection is actually bounded in LP for P between 1 and infinity. And to see that, let's argue as follows. I'm going to have functions of n+1 variables, and n+1 complex variables, and I'm going to write that as a parameterized function of real variables in the following way. And now you remember that the Bergman kernel is really a function just of the difference between the real parts and the sum of the imaginary parts. So there's a function capital K, so that the function, the Bergman kernel, is the function at this point depending on the sum of the imaginary parts at the difference between the real parts. And now if I write mu of S to be this height of the point SS above the boundary, what one can show using the estimates that we had for the kernel, that the L1 norm of this function can be expressed in terms of this function mu. And then it follows that, then I want to define an operator acting on functions. Now we're just in Rn+1, so G is a function just on the convex set sigma, and K of G, this I like to think of as some kind of a Hilbert integral. It's like the integral of f of y over x plus y dy from 0 to infinity. I'm integrating G at a point, and I'm looking at some kernel at y plus v. And then the Bergman kernel is simply the integral over sigma of the convolution of this operator with f in the variables x, and then integrated over all of sigma. Therefore, one can then look at the LP norm using the, one then easily gets the estimate that this P, the LP norm of P sub beta of F is bounded this way. And so the LP boundedness of the Fourier of the Bergman projection would follow from the LP boundedness of the operator capital K sub beta. Where does this come from? I claim that this now simply follows from Schur's lemma, and the following estimate for integrals involving the minimal volume. If I'm looking at something like this operator K beta acting on minimal volumes, and at least if the parameters are suitably chosen, if I integrate this way, then this integral is simply the minimum volume at 1 minus the sum of the two parameters, or 1 minus the sum of the two parameters. And from that, it follows from Schur's lemma that this operator is bounded. I might conclude by pointing out that formulas like this are very similar to formulas involving the weight functions that one sees in the study of tubes over homogeneous symmetric cones, where one uses weights of the kind that I indicated earlier. One has not approximately equal, but equal. So this perhaps suggests that there's something to these minimal volumes here. So with that, I think I'll stop, and thank you very much.